Good afternoon, everyone. Thank you for joining this presentation. Today, I'm going to talk about our work on reducing label cost in sentiment analysis via semi-supervised learning. We will discuss the challenges of obtaining label data for real-world applications, the opportunity presented by abundant unlabeled data, and how we can leverage semi-supervised learning techniques such as label propagation to bridge this gap. This is the outline of today's talk. I will start with introduction, then we will talk about the methodology we used and the dataset in details, and later on we go through the result and discuss it. Finally, we sum up with the conclusion. Labeling dataset is for machine learning task is fundamental, but expensive and time consuming. However, unlabeled data is abundant and cheap. So our motivation is to explore how label propagation, a graph-based semi-supervised learning technique, can significantly reduce labeling cost and enhance the performance of sentiment analysis models. The good thing about the semi-supervised learning is that even if our labeled data is limited, we can still have an idea of what structure the unlabeled data might have and gain a better understanding on the overall data structure when determining the decision boundary. Traditional learning models mainly try to find the relationship between the labeled examples in space. But in semi-supervised learning, we aim to use not only labeled data but also unlabeled data, including samples that do not have labels. Semi-supervised learning bridges the supervised and unsupervised learning by using a small set of labeled data and larger set of unlabeled data to enhance the model performance. The key methods includes the graph-based approaches, which they leverage the graph structure to propagate labels using relationship between data points. Graph neural networks like InfoGNN and transductive label propagation method have shown strong results in note classification and text classification tasks. Another approach is total labeling, which uses the model predictions on unlabeled data as labels, and it encourages entropy regularization and improving the class separation. The techniques like parse enhances this method by handling noisy labels through robust loss functions. Another category is the temporal ensembling and mean features, which combines the prediction across epochs or average model weights to improve accuracy while reducing dependency on label data. And finally, virtual adversarial training, which employs the virtual adversarial loss to improve model robustness without requiring label information. This study, we apply the transductive label propagation method based on the manifold assumption for sentiment analysis in text classification. Let's start with the basic idea. Label propagation is a graph-based semi-supervised learning method. Imagine all your data points, both labeled and unlabeled, as dots and vectors on the graph. Points that are closer together in the graph are likely to belong to the same category or share the same labels. So this principle is known as a cluster assumption. In this method, labeled data points act as sources or information, and unlabeled data points are assigned pseudo labels based on their proximity to labeled data on the graph. So in the training pipeline, we need a baseline model training. We start by training a simple model on a small set of labeled data. This model gives us a baseline performance to compare against. And then we need a feature extraction. We use this baseline model to extract features from the unlabeled data. These features represent hidden patterns in the data that the model has learned. In the label propagation step, we which is the exciting part, we create a graph where labeled data points are connected based on their similarity. Using this graph, we assign pseudo labels to the unlabeled data. These pseudo labels are guessed based on the labels of nearby points in the graph. With both labeled and unlabeled data in the hand, now we train a new model. This model learns from the expanded dataset, improving its ability to generalize. And finally, we refine the model by training it further on the combined dataset. This includes all labeled and pseudo-labeled data. This step maximizes the model performance. But how does it help? Label propagation is a form of transductive learning, which means it uses the structure of the data to separate labels. By including unlabeled data in the learning process, we can make use of available data and the model gains a broader understanding of the problem. And we reduce the need for larger amount of labeled data, which is often expensive to obtain. So this algorithm is the algorithm that we used here, and it summarize what I explained right now. For this study, we used the large movie review dataset, also known as IMDb dataset. This dataset is a prominent resource for sentiment analysis and NLP tasks. It contains 5K movie reviews split equally between the training and test set. The dataset is balanced with an equal number of positive and negative reviews. Why it is important? In many text classification tasks, class imbalances can be a major issue. If one classes dominate the labeled data model, especially those using label propagation, might make biased prediction. The balanced nature of the IMDb dataset ensures fair representations and avoids this pitfall. So let's talk about preparing and cleaning the data. So to ensure diversity, we shuffle the data set, and the data is then split into the training and validation set with a ratio of 80-20. And for semi-supervised learning, the data is further divided into labeled and unlabeled data set as well. For cleaning, we converted all data to lowercase. We remove leading and trailing spaces with separate punctuations and eliminate non-alphabetic and non-punctuation characters, and also cut down all excessive spaces. And for the text processing part, we tokenized and we convert the tokenized text into the numerical indices, which makes it easier for model to process. To improve the model performance, we incorporate pre-trained word vectors. These embeddings help the model understand the meaning of words based on their context. So pre-trained word vectors are loaded from a file. An embedding matrix is created to map words to their corresponding vector representations. And tokens in the dataset are mapped to either their pre-trained vector or if the token is unknown, a default vector. So to balance the complexity, we build a vocabulary on top of 10K most frequent tokens. This strikes a balance between capturing linguistic relevance and keep the model complexity manageable. So this is our results. Here we explore the impact of using pre-trained models such as word-to-vec, fast text, and GloVe on the model performances. These embeddings provide rich semantic information for initializing a baseline Biguru model with 64 hidden dimensions and 2 layers. In experiment, we used 10% of the dataset. GloVe 300 outperform all other embedding across metrics, followed by the fast text 300, and then GloVe 100 and word-to-vec 300. GloVe embedding, especially in a higher dimension like 300, provide most efficient capturing more meaningful information and achieving the best overall results. While word-to-vec had the lowest performance overall, it remained competitive during label propagation. Token analysis revealed that GloVe covered the most tokens, 8,725, and followed by the fast text 7,558, and for word-to-vec we have 7,064, which means that the GloVe's effective for high dimensional embeddings. We also compare the performance with a different number of tokens, which shows that 200 tokens consistently outperform 1,000 tokens across all three metrics for accuracy of one score and AUC work for both baseline and label propagation models. We ran experiment on three models, BiGRU, BiLSTM, and 1D-CNN, to evaluate label propagation and for the baseline model, and also for the fully supervised model. On 10% of the data, BiLSTM showed better F1 score and AUC walk, while BiGRU slightly outperformed in accuracy. In label propagation, BiLSTM excelled in accuracy, while BiGRU had a slight edge in F1 score and AUC walk. Although 1D-CNN delivered the best baseline performance across all metrics, it struggled with label propagation, while due to limitations in capturing long-term dependencies and generating accurate pseudo labels, which highlights the importance of model which highlights the importance of the model capable of addressing these challenges effectively. We have similar observation with comparing baseline and label propagation method using Rader charts. Both BiLSTM and BiGRU models perform agreeably with label propagation, followed by the baseline highlights its effectiveness. However, in models like 1D-CNN, label propagation may only sometimes be beneficial due to its sensitivity to less labeled data and ability to capture local patterns and features. BiGRU models have been found to perform well due to their ability to capture long-term dependencies and contextual information from both the directions in the text. BiLSTM models are similar to BiGRU's but can capture even longer dependencies due to the LSTM memory cell, which also helps mitigate the vanishing gradient problem. So, we have some key observations from the hyperparameter optimization results on the BiGRU model. Increasing the proportion of the labeled data from 10% to 35% generally improves the performance of label propagation method across all metrics. But as the amount of labeled data increases, the efficiency gain of label propagation over the baseline decreases. This highlights a trade-off in supervised learning. To sum up, we can say that while more labeled data typically enhances the performance, using too much can lead to overfitting, and it reduces the model's ability to generalize effectively. So, we also conducted additional ablation studies, which due to the time constraints, we won't cover in detail during this session. So, the key takeaways is that from this research is that label propagation effectively can enhance the sentiment analysis by leveraging unlabeled data, which demonstrated significant cost reduction while achieving performance near fully supervised models. And also, robust results with varied configuration and embeddings and model architectures are presented. The challenges that we identified is that the model is sensitive to data noise and graph structure quality, and it is dependent to the hyperparameter tuning for optimal performance. So for the future works, we are planning to extend the model to other NLP tasks and domains. We also plan to combine label propagation with active learning to label the most informative data points and hopefully improve the graph construction and pseudo labeling reliability. And finally, we plan to enhance the robustness of the model to the noise and imbalance data set. This is the reference list that we have. Thank you. Any questions?